Good evening. Welcome to the 7th Food Literacy for All. Two quick announcements. Just a reminder that the university is on break next week, so we will not have a class session. We'll resume the week after that. So March 7th with Linda Jo Doctor coming from the Kellogg Foundation. And students, if you're in the class, if you're enrolled in the class, your second essay is also due the next time we meet because of the break. So it's due on March 7th. I'll just flash this up here to remind you of what's coming up. And so if you're a community member here for the first time, just a reminder to RSVP on the website. And again, Linda Jo Doctor is next on the list. So that's it for housekeeping, did you have any announcements, Lily? All right. So I'm going to move on to introducing tonight's speaker. We're thrilled to have Dr. Timothy Cruz with us this evening. Tim is an ecologist, and he's the director of research at the Land Institute. Before I say anything else about the Land Institute, before I give it away, somebody just turned up my volume. I'm going to see what you already know about the Land Institute before Tim tells us about it in his talk. So get out your clickers, students. This is a very difficult question to start off the evening. So the Land Institute is A, land reform program in Latin America. B, was founded by Wes Jackson in the 1970s. C, promotes eating only fruit and nut crops. D, connects beginning farmers with more experienced farmers. Or E, has a team of corn breeders working to address environmental sustainability concerns. What do you think?
There's only one answer?
There's only one correct answer. All right, this is your 5-second warning. Pick a letter if you haven't picked yet. All right, go ahead, Katie. What did you think? Ooh, interesting. So the correct answer is actually B. It was founded by Wes Jackson in 1976. It's an organization in Salina, Kansas. That is a trick answer, though. It does sound like they might do that, and maybe you want to get into that line of work, Tim. That's a good suggestion. And then E was a trick question, so there actually are a team of plant breeders at the Land Institute, and that's the work that they do, but they're working on perennial crops rather than annual crops, and I'm sure we'll learn more about that tonight. So the Land Institute, in Tim's words, promises to transform agriculture from being an ecological liability to an asset. And I think hearing from Tim will provide a nice complement to earlier presentations by focusing more deeply on the production dimension of the food system, particularly on the dominant grain landscapes that make up approximately 70% of both human diets and agricultural land area. I actually met Tim for the first time at the Land Institute. We were both there in the summer of 2002. I was a research assistant. I was helping for the summer with a master's students project, and Tim was completing the tail end of a sabbatical year that was focused on legume nitrogen fixation in agricultural systems. And I found out when reading more about you today that Tim had actually visited the Land Institute years earlier when he was an undergraduate and was captivated by their vision and continued to track the work of the Land Institute throughout his career before eventually joining the organization in his current capacity in 2012. Before that, he had received an undergraduate degree in agroecology from UC Santa Cruz, a doctoral degree from Cornell University in ecology that was focused on biogeochemistry, conducted postdoctoral research at Stanford, and then developed an academic program in agroecology at Prescott College in Arizona. I already mentioned that Tim knows a lot about beans and legumes, in addition to writing some key papers that have expanded our ecological understanding of the nitrogen fixation process. I learned yesterday that, like many of us, Tim also loves to eat legumes. In particular, he really likes to eat tepary beans, which are an heirloom bean native to where he was living in the southwestern US, even though they're an annual crop. So we'll forgive you, that sounds delicious. So tonight, Tim is going to tackle an ambitious question. Can a sustainable food system be health promoting and economically viable and equitable and ecologically sound? I think I got all the ands. Thank you, Tim. We look forward to hearing from you.
Well, thank you. Thank you all for coming out this evening. I want to thank Jennifer and Malik and Lily and Katie and Mariah for putting together what is an incredible course that I'm now going to enroll in remotely in Salina, because I can, and I'm looking forward to the upcoming presentations. I checked out a few of them, and it just seems like a phenomenal course, so congratulations. So I'm going to start things off with a clicker question also. Essentially, I'm going to use the title of my talk for the question. Okay. At this stage of the game, I just wonder what you think. Okay, so 5 seconds. Oh, it's already out? Oh, okay. And so most people think the answer is yes. Gosh, well, that is good news. Okay. Well, I feel like I should have included a third answer, which I'm sure would have gotten 100% of the responses. We'll get this right, which is, it depends. And I have a feeling that at the end of this talk, you all will be there for sure. Most of the talks up till now, it seems to me, have focused more on the first three of these topics that are on the home page of the Sustainable Food Systems Initiative. Trying to balance health promoting and economic viability and equitability. And I've changed it from ecologically sound to ecologically viable, because I actually think that is a better way of framing the question for our agroecosystems. And so I'm going to be talking more about the ecological side of agriculture today, but I hope you'll see how it influences some of these other topics. And so I look forward to that. Hi, Malik. Welcome. As Jennifer said, I was a professor at Prescott College in northern Arizona for 18 years teaching agroecology, a summer semester that was a 4-course composite. Students enrolled in the entire thing, and every 3 weeks we would go on an outing to different farms, different agriculturally related enterprises, prehistoric agricultural sites in the Southwest, to the Central Valley in California. We went to the Land Institute, really stretched the margin of the arid Southwest, depending on the year, but we covered the gambit. And during 18 years of that course, for me, it was kind of a long walkabout. And I know it had a huge amount of impact on the students. Ethanol plants, we would visit 400-member CSAs in the Central Valley of California. But no visit impacted me or the rest of the students as much every year as visiting Hopi land in northeastern Arizona. Hopi land is fully encompassed by the Navajo Nation. But unlike many tribal lands where tribes were forced to relocate, Hopi have actually occupied these 3 mesas for over 800 years. And when you enter Hopi land, there's signs asking you not to take photographs. And so I don't have any photographs to show you, but this is Monument Valley in northern Arizona, and it looks quite a bit like this, just so you can get a sense of how arid the landscape it is. It is a desert. They get about 4 inches of rain in the summer and 4 inches of rain in the winter. Okay, it's pretty high though. It's higher than it maybe looks. It's between 5,000 and 6,000 feet in elevation. And here's kind of my rendition of what the maize fields look like. And it's an agriculture, as an ecologist, that just blows me away. It is arguably the oldest agriculture in the United States, continuously under production in this region for 800 years. Okay? No inputs, no purchased inputs. So how does it work? Well, they plant maize that is in bunches of 4, about 10 feet apart. And the plants themselves are rather bushy. They stand about 4 feet tall, and there's multiple stems, and they're typically leaning one direction away from the prevailing winds. And the seeds are planted 16 inches into the ground. Not with plows, by the way, they don't plow for Raj Patel's class. They use digging sticks. And it's a matrilineal society. So I don't know. I mean, he drew that connection, and that was pretty interesting. But come to find out that the nitrogen budget of this agricultural system is hard to understand. There are no, I should say, this is all maize. There's no intercropped legumes in a traditional Hopi agriculture. There's lima beans that are planted off to the side. But the maize is planted in the same place year after year typically, and sometimes there's a fallow thrown in every 4 or 5 years where no maize is planted. And there's almost no detectable organic matter in these soils. They're wind-blown, sandy soils. It's like planting into kind of a blowing sand dune. And so many of us have wondered how it is possible that they have harvested typically on the order of 25 to 30 kilograms of nitrogen per hectare per year. And the only inputs into this system that are obvious are from atmospheric deposition. From when lightning strikes, you do have a little bit of nitrate made available in the atmosphere, and it comes down in rainfall. And in stations in the region, there's about 7 kilograms of nitrogen per hectare per year that are deposited. But there's this huge imbalance of fertility that we don't understand. It did lead me to think that there may be what's called endophytic nitrogen fixation in the stem of the Hopi maize. And we were invited by Eric Polinguma, our colleague there, to look at that and have seen it. There is evidence that that's going on. But I'm not really here to tell you all about the nutrient dynamics of this system other than to marvel at it. Oops. And to suggest that the culture is equally fascinating to the agriculture in Hopi. And I'm no expert whatsoever, but it is clear that the ceremonies that are fully woven into the agricultural cycle are incredibly developed and continue to go on today. And some Bahanas or outsiders like myself are invited to some, and some are completely closed off. But the agriculture, again, truly, I think, is probably an example of an agriculture that is health promoting, has been economically viable within Hopi economy, equitable and ecologically viable for as long as any agriculture has been around, certainly in the US. Again, 800 years. However, it is struggling mightily today. When I went there with my class, we would go to weed a field, or we would go to harvest. We would go to do activities that were normally conducted by groups of youth from the community that would move around from field to field and undertake these tasks, as well as planting. And that no longer happens, at least not in Kaikotsmovi, where we were. Youth are typically off getting jobs, going to school, and the native agriculture is suffering for it. And there's predominantly older farmers doing the traditional farming. And we were left wondering, how long are these practices going to be carried on? And I use this as an illustration because Hopi agriculture is incredibly sustainable at growing food. But like many agricultures that have proven their sustainability, it does not allow obvious entry into the economic system of the United States and the level of consumption that a high energy society, a fossil fuel based society, requires. So you cannot buy a truck with a hectare of Hopi corn, but you can feed people for hundreds of years with that hectare of corn. So in some ways, I should have made the question, is it possible in the US economy of 2017 for a food system to be all of these things? Because I think it proves that it can be all of those things for a long time in certain cases. So I want to talk more about energy. In some ways, agriculture is an energy acquiring activity. Back 10,000 to 18,000 years ago, when agriculture first started, there's great debate as to when that was, but a long time ago, clearing land and putting our crops over more of the Earth's surface captured more of the sunlight and converted it to food for our species, right? And before what I refer to as the fossil fuel bonanza, before the discovery and exploitation of fossil fuels, agriculture had to abide by kind of a law of physics. You had to have a positive energy return on investment. In other words, you needed to derive more energy from your crop than you spent working to grow the food, right? It just had to happen. If you got less energy at the end of the year, less calories than you spent, you would obviously starve. And so many indigenous and traditional farming systems were brilliant in the way that they faced profound limits, such as in Hopi, to achieve a workable ratio of work to food produced, okay? And the range tended to go from 10 to 40 calories back for every calorie that was spent in work. And those extra calories were used to subsidize, things like warfare, which did not produce calories in and of itself. Religion does not produce calories in and of itself. And so all of these human activities are sponsored by the surplus calories generated in your agriculture. And the more surplus you have, the more extra agricultural things you might be able to pursue. Then we kind of hit the fossil fuel bonanza. And we went from an agriculture that relied virtually not at all on fossil fuel inputs to one today that, if it's maize in Iowa, relies almost 100% on fossil fuel inputs to produce the maize. So in other words, between the tractor and all the nitrogen fertilizer and everything, the only calories being burned by the human is the person in that machine farming some 5,000 to 10,000 acres, right? A remarkable transformation of the food system. For the first time, an animal sort of decoupled from this energy return on investment. The agriculture no longer had to pay for itself energetically. People follow what I'm saying? I said, okay. And this is a huge sustainability issue, I would suggest. And it's true in organic systems as much as it is in conventional systems, the dependency. Indeed, we have learned how to apply fossil energy to virtually every limiting factor, every ecological limiting factor in agriculture. Insect pests, weed competition, disease, water limitation, nutrient limitation, even increasingly temperature. And organic agriculture especially is good at using fossil fuels to moderate temperature with plastics and row covers and all sorts of cool devices to transform the local climate. So let's think about energy a little more with respect to gasoline. If we could take out those devices. A gallon of gasoline contains the work equivalent of how many hours of human labor? Okay? 5, 10, 50, 100, 1,000. Okay, so 5 seconds. Okay, what do we got? Ooh, good, okay. Well, 43%, it looks like, got the answer that Pimentel arrived at Cornell. And I've studied this number a bit because I didn't really believe it when I first read it, but this is not an alternative fact. This is real. And if you don't believe it, try individually pushing that 3,000 to 4,500 vehicle the 34 miles that you would drive it on that gallon of gas. It is remarkable the quality of energy that we have come to rely on throughout our economy, but it's thoroughly embedded in our agricultural production systems. So let's think about that in terms of economics. 100 hours of labor contained in this for $2.10 versus at $7.50 an hour, a low minimum wage, we're talking $750 to accomplish that amount of work. So we got, this thing. Okay. Let's see. I don't know. Which are you going to take? All right. And then go ahead and ratchet up to a living minimum wage of $15 an hour. And we're talking $1,500 to accomplish the work that can be accomplished in this. So not surprisingly, in agriculture, as anywhere else in the economy, any place that we can substitute this, we've done it pretty much. And then when this does not do the job, we will go to the lowest possible paid worker to do what humans have to do. And that is largely true in our food production system, except in places that are unique and trying to run against the current, like folks in this room. But certainly in the Central Valley of California, that's the case. And it explains a trend that Ricardo Salvador talked about in his talk a few weeks ago. And he didn't have this exact slide, but essentially it was showing that there's lots of small farms in the US, and there's very few larger farms in the US. And he was suggesting that the Secretary of Agriculture was saying, well, really, the only economically viable farms is this 12% out here on the end, which constitutes about 0.1% of the US population. These are the ones that, make over 200 or 300, or the 200,000 or 300,000 farmers that make over, I'm trying to remember what the number was, but it was hundreds of thousands of dollars of gross income and a living salary or wage in a net income. And this is because these are the farmers who are employing, if I dare say, the most fossil fuel slaves. So, I'm almost finished with the clicker questions, but I got into it. At the dawn of the fossil fuel era, which percentage of humanity was working in some form of slavery or servitude? And this is according to Paul Gordon Loren, the Regents Professor of International Relations, Diplomacy, and Human Rights at the University of Montana. A number I was very interested in, okay, because how much of humanity was essentially under someone's thumb, predominantly in agriculture, before the advent of fossil fuels? Okay, we're closing the poll. So C, 52, that's close. It is 75%, according to this professor. Now, this is a fuzzy number for sure, but I emailed him and asked, you really believe this? And he's like, yes, I do. And that's about as far as I've gone into it. But it is fascinating. It is fascinating because as we talk about pulling out of the the fossil fuel dependency that we have in the face of climate change, we have to realize where we've been in labor and food production to design systems that are egalitarian under much more intense limits, I would suggest, than we're used to even entertaining in the fossil fuel bonanza that we're living in today. And it's one of my two significant observations to convey to the class today, that a lot of the local food initiatives and sustainable agriculture initiatives do not pay nearly enough attention to the energy that is being used to create otherwise what is a non-toxic, egalitarian, economically viable, healthy system. So energy is a big deal. And the last one of these numbers I'll put up is just that by my calculation, and this has been corroborated by another researcher, about if you take the commercial energy of the United States and you divide it up by the population, and this is definitely crude, but it's for the sake of discussion, 80 people, there's 80 fossil fuel slaves of energy equivalent working for every citizen of the United States. Obviously, you can't convert fossil fuel into, you can't convert human labor into plastics or flying an airplane or other things that we use fossil fuels for. But again, just to give an understanding of how far out we are with this energy source as we think about landing back on the planet in a sustainable agricultural system. In essence, we've gone from Homo sapiens, the thinking human about how to live within limits, to indeed Homo petroleus. And I put up a picture of Wes Jackson, no less, as the Homo petroleus. So, all right. Now I'm going to shift gears. That was energy. Now I want to talk about the relationship we have in agriculture with our ecosystems. At the Land Institute, we talk a lot about how natural ecosystems function, how they've evolved on the landscapes over time. And there's a couple of characteristics that are very common across virtually all natural ecosystems. They tend to be overwhelmingly dominated by perennial plant species, and they tend to have numerous plant species in the communities. And this contrasts significantly with our especially grain production systems, and especially industrial grain production systems, which tend to have one species and even one genotype of crop, and that crop happens to be annual. All of our grain species are annuals, which requires this ecological catastrophe to happen on an annual basis, a pretty much wholesale clear cut of all of the other species on the landscape, so as to allow a chance for our annual seedlings to emerge and thrive year after year. So by eliminating diversity, we eliminate a lot of the functions that allow natural ecosystems to exist. Diversity tends to confer all sorts of things that agriculture has had to make up for with inputs, okay? At least this is the premise. This is kind of the point of departure of the Land Institute, and in many ways, these are hypotheses that we work through in our work. We're often asking ourselves, well, how much diversity do we need, and of what type, and how is it deployed on the landscape? There's no easy answers, but it's quite clear that this does exist in natural systems, and to a much less extent in our agriculture. This, by the way, is recognized deeply by most agroecologists. There's been a lot of work on diversity in agroecology over the years. However, this side of the coin has received much less attention because the answer is problematic and not as obvious. This is work by David Montgomery, who in a proceeding of the National Academy of Sciences paper compared rates of soil formation, and these are global medians, very big median numbers. At 4/1000ths of a millimeter, soil is being formed across the planet. Whereas in plowed agriculture, it's being lost at about 1.5 millimeters per year, global median, over 300 times the rate of soil formation. And then in no-till agriculture, soils are being lost at quite a bit lower rate, maybe 15 or 16 times the rate of soil formation. But what's clear from this is that agriculture has depended profoundly on the soil capital that was built under the natural ecosystem, and that we continue to exploit that, but it's not being formed, at least not in most annual agricultural ecosystems, if any. So my final clicker question is a repeat question from Francis Moore Lepay's talk. Okay, so you better get this right. How many pickup trucks full of soil are eroded per person on the planet every year from agricultural fields? 1, 2, 3, 4, or 5? Okay, 5 seconds. All right, what do we got? Okay, well, not bad. A thin margin got the answer that she provided was 4. But it's a phenomenal amount of soil to imagine that eroding from agricultural lands for every human alive every year. But that's not a recent phenomenon. There's evidence that soil erosion contributed to the fall of many ancient civilizations on the planet. And these are ancient civilizations that were mostly local, organic, growing heirloom varieties on small farms. Okay? Now, I'm not saying that these efforts are misguided. I'm simply saying that they are insufficient in the face of the problem. But it's not just soil erosion that happens when you till or plow land. It's also the loss of soil organic matter. This graph show on the x-axis is years of cultivation, and on the y-axis we have soil organic carbon remaining. And so over the first decades, you have a significant drop in soil organic matter as tillage proceeds. And this brackets the range of most soils. Most soils lose between 25 and 60% of their soil organic matter after they've been cultivated for decades. Okay, and why is this? Well, one reason is that when you till, you break soil aggregates up and expose what is referred to as physically protected organic matter. You expose the soil organic matter to microbial attack, and microbes just go nuts, and they eat up a lot of soil organic matter, and they breathe out a lot of CO2. And in fact, the first huge human contribution to greenhouse of carbon dioxide in the atmosphere came about from agriculture and land clearing, not fossil fuels. But the other way that soil organic matter declines is because we replace perennial species that allocate about 40 to 60% of their organic matter below ground with annual species that allocate between 15 and 25% of their productivity below ground. And root biomass is thought to be the primary organic matter that forms stable soil organic matter, okay? And soil organic matter is like the holy grail of organic agriculture, of agriculture in general. I mean, agricultural development organizations think long and hard about how can we possibly raise soil organic matter to improve many aspects: water holding capacity, nutrient supplying capacity, disease suppression. All sorts of aspects of farming systems are affected by soil organic matter. So then other things are lost from plowed agricultural systems as well, organic and conventional. Between 30 and 60% of the nitrogen fertilizer applied to grain fields is not taken up by the crop. It either goes up in the atmosphere as nitrogen gases, including the greenhouse gas nitrous oxide, N2O, or it is lost through nitrate leaching. Now, there's no question that cover crops, the integration of cover crops and some other practices, will greatly improve on this situation. But whenever you have to expose the soil like this at some point in the year, there's a pretty vulnerable window for nitrogen loss, exceeding what probably should be allowable. Consequences include the formation of dead zones like that forms at the mouth of the Mississippi River every year, the size of New Jersey. They hate that. But it is essentially when you fertilize the water column of the Gulf of Mexico, a huge algae bloom happens. It consumes oxygen, and the whole system crashes. And this happens at the mouth of over 140 rivers, major rivers around the planet, predominantly due to agricultural nutrient runoff. Why? Because they're leaky. There's huge times of the year when there's no roots in these soils taking up water and nutrients. Oh, I keep hitting that wrong button. Weeds. I'm just going down the list here. Weeds occur in agricultural systems when there's unused resources of sunlight, nutrients, or water. And so this is, if you look at your driveway and you have like a square centimeter, there's a weed there typically. They're incredible at finding and exploiting little bits of resource. But look what we do. I mean, this is the biggest welcome mat. The reason we plow in the first place is to get rid of weeds, but then paradoxically, it is the ultimate weed habitat that we form. And so either we plow, and that carries with it the risks of erosion I've already talked about, or increasingly, we're relying on herbicides to take care, at least in grain agriculture in the Midwest. A majority of grain crops are Roundup Ready, herbicide-tolerant crops. And I think, as this class probably knows, there's a large number of weeds that have become resistant to Roundup. There's concern that Roundup itself is carcinogenic. And we're starting to create new cocktails of herbicides to replace Roundup, which is no longer very effective, that may carry with it all sorts of endocrine disrupting activities and other health impacts. So I guess what I'm saying is to maintain this agriculture in this state over time, it requires a lot of energy to keep it here, and then it takes a lot of energy to compensate for the lack of function here in applying nutrients, applying herbicides, plowing it, and so on. Okay, so I'm going to let you in on something. When I was an undergrad, I saw Eugene Odom speak, and he's a well-known ecologist. And he was talking about agriculture, and he said, if we could just eat the fossil fuels directly, we would save so much land from agricultural degradation. So my wife, who's here tonight, Sarah, and I began when I was in graduate school with an experiment. So it's a long-term experiment. Our daughter, Ruby, we started feeding her straight Valvoline, and the early results, we would change the weight from time to time. The early results were criticized with n equaling 1, and so Claire came along and got through the awkward teen years, a little Camelback. I mean, can you imagine having to tolerate this your whole life? Your dad being obsessed with this, but anyway, so yes, that is one possibility. But I'm here tonight to say there is a better possibility, okay? And that is to take this agriculture that in ecological terms is incredibly disturbed. We're holding this ecosystem at an early stage of succession, which ecosystems just don't do. Ours is really the only one. And moving it through succession, and when we move it through succession, we will see greater soil protection, carbon and nutrient retention, weed suppression, and I'm not talking about it tonight, but there's reason to think that there will be an improved, more highly functional soil microbiome, okay? Now let me give you just a quick illustration of what this would look like. Some students in the class read a paper by Glover et al. In 2010, and Jerry Glover and some of us measured attributes of a prairie hay meadow, 5 of them in central Kansas. Farmers have hayed these meadows for 70 years or more with no fertilizer inputs, okay? And meanwhile, on adjacent land, they're farming winter wheat. And this is just a little bit of the nitrogen story behind these two ecosystems. The prairie hay meadow over here receives no fertilizer. Annual wheat receives about 70 kilograms per hectare per year. The N export in the harvest is almost identical. You're taking off about the same amount of nitrogen in the hay as you are in the wheat. So right there, 47 divided by 70 means the annual wheat is able to captivate around 34% or 66% of the nitrogen, and 34% is going somewhere else. Okay, that's on the low end of that figure I gave you earlier, right, between 30 and 60%. However, if you look at the total soil nitrogen in the organic matter left in these two systems after 70 years, you find out that there's, bizarrely enough, quite a bit more nitrogen in the prairie hay meadow soil than there is in the wheat field, even though you've applied no nitrogen fertilizer to this prairie hay meadow, and you're applying 70 kilos per hectare per year to the wheat. So if you take into consideration this decline of soil nitrogen that's being secretly pumped into that annual wheat every year, you end up seeing a fertilizer uptake efficiency of only, or nitrogen uptake efficiency of only 40%. In other words, the wheat is only utilizing 40% of the nitrogen that's being made available. 60% is either going up or it's going down into rivers. It's going somewhere else into the environment. That's both very economically expensive for the farmers and very environmentally damaging for the ecosystem. Jerry went on to compare the energy required to maintain that prairie hay meadow as a farmer, compared the energy required to maintain the annual wheat. And we're like, we want an agroecosystem, we want a farm that looks more like this. How do we do that? Well, as you know, we can't eat this. Livestock can eat this, and releasing livestock on perennial pastures makes a lot of sense in this analysis. However, for grain, we can't eat this. And that's the work of the Land Institute right now. We need new hardware, new crop hardware. This is a laptop computer. Built on early 90s hardware. And, you know, it's not so far-fetched to say this is what we're trying to do with sustainable agriculture right now in the way that I've been talking about it, using this hardware. And so we need better hardware. And clearly, what's missing is perennial grain crops. And so this is our Kernza crop growing over 4 seasons of the year. That's on the right. This is a wheat relative. its root system, compared to annual wheat, which is on the left. And in September, there's nothing there, right? There'd be a seed planted in about a week right there in September. And then you can see the wheat root juxtaposed against this nutrient and water vacuum that exists as a deep-rooted perennial species as a comparison. So there's two different approaches to breeding perennial grain crops that we're taking. One is domestication. We're domesticating an oilseed crop, a kernza crop, and we're about to embark maybe on a legume. We've hired a legume breeder. He is in a discernment mode as to which crop he should be working on, whether it should be a domestication or white hybridization. White hybridization, which I'll briefly mention first, is sorghum, wheat, rice, which colleagues in the Yunnan province of China have developed, and maybe a legume there as well. So what does this look like? It's by white hybrid cross, I mean we will take an annual crop that's already existing, like wheat, and cross it with a perennial cousin, such as intermediate wheatgrass, which is also kernza. It's a little confusing. Or sorghum with what is otherwise a noxious wheat, Johnson grass, as a perennial cousin. And the same is true with rice. And so it's crossing species that will cross naturally and arriving at a hybrid that then you work with back crossing. In fact, I have a few slides to show you how perennial sorghum works. This is the annual grain sorghum, and this is the perennial cousin, okay? So you cross those two, and you get something that looks like this in the first generation, okay? And then you'll take this plant and cross it back to this, the grain sorghum, and you'll get something that looks like this. And this process goes on and on and on as we try to arrive at something that looks really close to this and has the seed quality and almost all characteristics except that it's perennial as opposed to being annual, okay? This is perennial sorghum sprouting in the spring. These are rhizomes, underground stems that re-sprout and produce the perennial plant, such as sorghum. Otherwise, a crop that you would have to resow by seed in the spring. And this work is, I am not a plant breeder. You have to be highly organized to be a plant breeder. This is Stan Cox, plant breeder extraordinaire, and there's lots and lots of keeping track in the breeding program. The sorghum is being trialed in various parts of sub-Saharan Africa, in Uganda, in Mali, Ethiopia, and South Africa. And in Uganda in particular, where a lot of the work's being done, there's actually a breeding project going on there where you would cross, or where they will cross, landrace varieties of sorghum with the perennial germplasm to try and arrive at a sorghum that is well adapted to those conditions, especially adapted to getting through a dry season rather than a cool season like we do in the temperate latitudes. Perennial wheat, as I mentioned, is a cross between intermediate wheatgrass and annual wheat. Xuan Wang is in charge of that. A lot of very delicate work because annual wheat is an inbreeding plant, so you have to emasculate the wheat, pluck all the stamens out of the wheat, and take the pollen from the kernza or the intermediate wheatgrass to make these hybrids. But we have been successful at obtaining hybrids that re-sprout after the growing season and producing multiple crops. The perenniality is not stable in these wide hybrid crosses yet, but the projects have only been going on for decades. Okay, and that sounds like a long time, I know, but boy, all the other crops that we eat took hundreds of years of domestication to get to where they are. And the work that we're doing is progressing quite rapidly from a plant breeding perspective or a new crop development perspective, but very slow in our society's mindset. And that's the hard part. Perennial rice, just briefly, is, like I said, is being developed in the Yunnan province of China and is the furthest ahead of all of these crops. There have been 3 harvests, 3 years of 2 harvests per year of rice that approaches the yields of the annual paddy rices in central Yunnan. And it's delicious, actually. We ate it last time we were there. So in terms of the other strategy of domestication, this is not involving wide crosses. This is actually a process that the Neolithic farmers used to develop the crops that we eat today. And that is just rounds and rounds of selection on the best plants. It's a little more involved than that, how we do it, because we actually very specifically cross individual plants that we want to cross. But here you can see the wild sunflower from which our modern sunflower was domesticated. And so we are doing the same things, especially with this crop here, silphium, a native prairie plant to the Midwest. Those are its seeds. And through rounds and rounds of selection, we expect to create not necessarily that kind of crazy monstrosity of a seed head, but something that yields well and provides an oil seed, an oil crop. And here is why we're after this plant in the first place. It is almost not fazed by drought. 2011 and 2012 were extreme drought years in the Midwest, and it hardly blinked. It's an incredibly lush plant. Weaver, the botanist, just spoke at length about it in the Dust Bowl. And we're very excited at it being a climate-hardy future oilseed crop in various parts of the world, actually, but definitely in the Midwest U.S. There is some other photos of it. More keeping track. Kernza is the domestication crop, and this is the last one that is getting the most attention. I don't know if anyone heard of the beer that's come out made of this. It's called Long Root Ale. You can't get it here. You can't get it in Kansas. It's only available on the West Coast right now, made from Oregon Hop Works. But it's being gradually, initially commercialized as we speak. And this is a picture of a large breeding field of Kernza, 25,000 plants planted out, looking for needles in the haystack of individual plants that have traits that are exciting. I won't list what we're looking for, but the plants that have them get folded into the breeding population, and then you proceed with another round of intermating and selection. This is just showing that the size or the seed weight is moving to be higher and higher. And the maximum seed weight found in the breeding populations keeps getting higher. And this is just, again, selection for the highest yielding species from what was a wild grass when we started. It can be combined, speaking of using fossil fuels. If you're going to be economically viable agriculture in the Midwest, you cannot harvest wheat by hand on any scale. You certainly can for certain applications, but the people do not exist in the Midwest to harvest that much wheat. It's been pretty depopulated. Kernza can be grazed. And I should say that once these perennial crops are developed, we're not interested in planting them out in vast monocultures on the landscape, but are very intent in developing functional polycultures, bicultures or polycultures. This is one that I work on a lot, in which we have alfalfa as the most robust intercrop species to plant with Kernza as a nitrogen source and a disease break. Very wordy slide to end with, but the take-home message is that there's many ecosystem services associated with intact prairie in our part of the world. And that as we moved into this era of a highly, highly disturbed agriculture, an industrialized version of it in the last 200 years, many ecosystem disservices are associated with our food-producing ecosystem. And it's our intent to continue moving this further down the successional gradient to where we may have moderate diversity, but perennial crops that then can once again recapture many of the ecosystem services that existed in the natural ecosystem while maintaining food production that exists currently on the landscape in grain-producing regions. We're not doing this alone. There are many collaborators around the world, and would love to invite some of you to join the crew. So with that, I think we will come up and have a little panel and take some questions. Thank you so much.
Did you get a mic? I guess there's one chair. Are there any other chairs in the back of the room? No, stand there behind you. Oh.
Are they behind here? Oh, yes. There they are.
How sneaky. Thank you, Tim.
Okay.
I think they usually turn them on in a minute.
How are you?
I might actually kick things off with a quick question because I know a lot of students, it's on, can you hear me? So a lot of students in the class were interested in the nutrition dimension of the food system as well, and when you went through the crops that you're breeding at the Land Institute, you didn't talk about the extent to which nutritional quality is a part of the breeding program.
Yeah, every one of the crops is quite different in where it stands with respect to nutritional quality. Some of the domestication efforts are actually requiring that we breed out anti-nutritional compounds. So for example, the legume breeder is very interested right now in working on lupins. But lupins have some secondary compounds that are pretty toxic, and when people eat lupins right now, I ate them once in Bolivia. They were thoroughly leached and steamed, and yet Australians have actually succeeded in breeding those compounds out in annual species. So it seems feasible to accomplish that. Many beans actually have anti-nutritional compounds, as we know, but we still love them. And things like Kernza, it's interesting. Kernza is very high in protein because it doesn't have the endosperm with the carbohydrate in it. The seed size is not nearly as big as annual wheat. And annual wheat has bulked up in that end of things. So when we fold Kernza flour into with wheat flour to bake with, it strongly improves the protein content and the fiber also. But it's fairly similar to wheat. It does have glutens that disappoints a lot of people, so it's not a gluten-free, but it doesn't have the right glutens at this point to cause bread to rise. It's synergistic with annual wheat, and so you can mix them 50-50 and it makes a beautiful loaf. But yeah, and then the oilseed has a profile very similar to sunflower, actually, is what we're finding. Although it's interesting introducing a new food species because no one wants to touch it. And we're undergoing, the Patagonia, actually, the clothing company, is who helped move Kernza into that Oregon Hop Works. And they spent a lot of money to eliminate liability on Kernza, even though that plant had been used to cross with wheat to pull traits out of the perennial into the annual historically. So people have been eating intermediate wheatgrass in wheat for some time, but that was not enough assurance, and so a lot of tests were run on human allergic reactions or any other issues that are of concern. So as we develop new crop plants, I think we will be faced with having to show that they're innocent, and not that we have to wait till they're proven guilty. You have to prove that they're innocent.
So who owns these new hybrids when you're mixing perennials and annuals? Are there patents on them?
We do not patent any of our germplasm, and it's becoming harder to keep germplasm, or I call it seeds, in the public domain. But you might have seen that we've trademarked Kernza, and that is the name Kernza. And so if people call it Kernza as it moves from the farm into the mill, we will get a couple of % of the value to help fund the research. And Kernza is by no means finished. There's a lot of work to be done on it, and so that's how we intend to help fund the research. However, if a farmer obtained Kernza seed and grew out a field and then took that seed and wanted to plant it on another field, they completely can do that. There would be no private rights or proprietary rights to make them have to fill out another contract and pay more to grow more acreage of Kernza. And so so right now we own it, but we freely distribute it to other researchers to have it worked on. And our hope is that more and more plant breeders do take up the calling and develop either new crops or work on our stuff, or hybrids being developed by other organizations to have well-adapted species for a broad range of geographic locations.
Here and then here. Wait for 1 second for your mic.
Yeah.
Might wish I hadn't had the mic.
Uh-oh.
As I was listening to you, I just couldn't help but think Monsanto must be pissed. I mean,
Well, so, I mean, we hope so. But unfortunately, I should say this, but I don't think they're quite pissed yet. The statement was that she couldn't help but think that Monsanto must be pissed at this work. And it actually explains, in part, in our minds, why it does not exist yet. I mean, if you're developing an agriculture that does not need to be re-sowed every year and does not require herbicides, and it doesn't lose nutrients like crazy and all of these other things, what's there to like about it if you sell all of those, right? And so truly, I mean, I do think that is partly why it does not exist from another region of the economy. But I'd say at this point, we're not large enough to make them too mad. But I do think someday, I hope that it causes some consternation. Yeah.
Hi, thank you so much for your talk. It was really interesting and persuasive. I had a question about your philosophy and the Land Institute's philosophy on incorporating molecular or genetic techniques into this type of research, and whether that's been pursued, and if not, why not?
Right. Well, we do employ a lot of what you might call marker-assisted selection. We use information from the plant's DNA to inform the breeding process. So all of our work is still happening with cross-pollination, as happened with traditional plant breeding, but we, in all of the crops, are laying out large fields in which we correlate different traits we're interested in with chromosome or genes on chromosomes. And that is an approach that, if successful, and it's really just getting going, but it is getting going, could accelerate this work substantially to where we may just need 10 or 20 years to develop a new crop rather than 30 or 40, for example. Perennialism itself is a very complex trait controlled by numerous genes, and no genetic engineering at this point is up for tackling that. And if it were, the capital and the companies that would need to be access to do that work would want to own it. And so we haven't been interested in going there. Right now, traditional plant breeding is the approach that we are interested in using. We do have conversations about more subtle genetic techniques like cisgenics, about crossing, moving a gene from two related species that cross naturally, like I was talking about these wide hybrid crosses. One of Wes Jackson's best quotes in my book is that critical thinking ends where fundamentalism begins. And so we are trying to drop an absolute black and white in the discussion around molecular tools in plant breeding. They are not all the same. And it's interesting to ask yourself, well, gosh, if these plants cross naturally, and you cross and then you spend 10 or 15 years trying to get rid of a lot of the genes that came over from that wild one, what is the issue if you move that gene over between these plants that naturally cross? I think it's an interesting discussion. We don't do it, but we can see stuff like that out there, and we are scratching our heads trying to decide what we think of them. And we welcome conversation on those topics. Yes.
Over here.
In your hybridization efforts, you say that you achieve perennialism in certain stages, but it's not stable.
Yeah.
Can you comment on why it's not stable?
It varies from crop to crop. It has, like I said, it's a bit of a relative definition of perenniality. The rice that I was referring to has proven to be productive for 3 years, and there's no reason to think it won't be 4 and maybe diminish at 5. We don't know with the current hybrids they have. It differs from species to species. There's issues in the wheat. We think with this is probably more than most people want to know, but I'll be quick. With the flowering time gene, a good perennial will produce a crop and then shift back into vegetative mode for the rest of the growing season. And in the case of wheat, it'll go through the winter, it'll vernalize, and then produce another crop, then shift into vegetative mode. But the wheat hybrid, actually goes through the winter. It'll produce a big crop of seed, and then it continues to stay in the vegetative or in the reproductive mode, which is inherited from the annual wheat because its other parent is Kernza, which we know does very well at being a perennial. And so figuring that out and looking for plants that have the other parent controlling that is one of Shuin Wang's strategy to help what I'd call stabilizing the perennialism. So that's the example of wheat. There's other challenges like that for the sorghum, which mainly has to do with how deep the rhizomes grow. They don't go deep enough in the soil to get through the Kansas winter. They're far more perennial in Georgia, where our colleagues are also growing it out. But one thing that's for sure is that when you do the domestications, that you start with a really robust perennial like Silphium or Kernza, it's perennial. And there you're just selecting, like we did with all of our other agricultural crops, for plants that don't drop their seed at the end of the growing season. A very elementary domestication trait, that has to happen. So things like that.
There's a lot of hands at once. You had your hand up before in the center there with yeah, Mariah.
Thank you for your talk, Tim. You mentioned that perennial crops can be used to recapture some of the natural benefits of the land. And I'm wondering how well you think the switch to perennialism could be used on land that has already been tilled and planted with annual crops.
And been planted with what crops?
With annual crops. Sort of like restoring degraded land.
Yeah, we think that the perennial crops could really help in that respect. There's a lot of interest in recapturing carbon that was lost from soils now. I don't know if you've heard about it. And a lot of what people are suggesting it's unproven. Biochar will certainly increase soil organic matter. But by coming up with an agriculture that resembles the native vegetation that built that soil in the first place, a mollisol in the case of the Midwest, these grassland soils. Absolutely. There's very good reason to see improvement in soil health, both in soil structure, how water infiltrates into the soil, the amount of soil organic matter it captures, and all of the soil microbiome. There's really cool work that shows that, for example, later successional mycorrhizal fungi, these are fungus that infect plants and help them take up phosphorus and do all sorts of neat things, that the mycorrhizae that show up when a soil hasn't been disturbed for some time, which you see in later successional prairie plants, tend to be far more efficient than the kind of weedy mycorrhizae that exist in annually tilled systems. And so that just gets me pretty excited to think of, Jennifer was on a paper that was published last year called Going Where No Grains Have Gone Before. From moving down the successional gradient, there's so many things that may happen in a soil that we've never been able to touch in annual agriculture. So yes, I think it's a fantastic restoration approach that could be used over large landscapes.
I'm going to, in the interest of time, just ask one
Yes.
thing from a student that was posted on Canvas, and then we'll take a few more just to shift gears and make sure we cover all the bases. So one of the students in the class wanted to know, from your perspective, what can scientists do to support and establish new agricultural policies and be active in the political realm while also doing research? So thinking about the implementation end of what you're developing.
So wait, say it one more time.
What can scientists do
What
to
can
support and
scientists do?
establish new agricultural policies?
So why don't you, I want you to answer that, Jennifer.
I was hoping
I've been
you would
talking a
answer
lot.
it, Tim.
but I mean, I'm curious. Like, for example, what are you thinking?
Well, I think a lot of us in this room, especially students who've taken the food systems class, were well aware that there's so much beyond just providing evidence, right?
Yes,
That's
right.
involved in implementation.
Right.
And we've talked a bit in this course about the need for things like grassroots action to put pressure on policymakers, as well as the need for supportive policies that would, for example, shift public dollars towards
Yeah.
the types of programs that you're talking about. But I don't know if the Land Institute engages in either of those ends of the spectrum.
I will be at a listening session in Washington in about 10 days where the USDA has invited researchers to come in and talk about work that would further long-term sustainability in agriculture. It's a very unique session as far as I can tell, and we're very excited to be a part of it. We do not actively engage in lobbying or policy efforts to any great extent. However, I mean, there's no question that some of the subsidy programs and a lot of what I'm sure you've talked about already, in fact, I've seen it being talked about in previous talks here, we would be equally behind those changes, because anything that's holding the landscape in its current production mode is problematic, and there is a lot of policy that holds it there, as we know. And so we are not ourselves involved in that, but absolutely that would be one place for scientists to apply pressure.
Yeah, Andrea.
So it was really interesting to hear about the ecological research that you've been doing and ecological nutrient management as a whole. But given how you started the lecture with that big question, I'm wondering how you envision, so like after all these ecological discoveries are made, let's say like in 20 years or whatever, however long it takes, how do you envision that this is gonna start to how do you envision that our food system will actually transform out of the dependency on fossil fuels and industrial agriculture, given how dominant it is, and not just on a policy level, but also energetically, as you were speaking, we've become so entrenched in the system. And while these research initiatives are very, very cool and very interesting and have a lot of potential, I'm wondering, like, logistically, and how do you envision like small farmers are just going to start planting these perennials? Like, how is this going to?
Great.
Okay.
Yeah.
Thanks. I guess I feel like Homo sapiens, we're really impressive up against limits. But we're not very good at setting them. And so that's the dilemma I see with our response to climate change right now. We just do not seem to be able to react. But if there are limits, if they arise, we can do phenomenal things. And I guess part of my response, just as a person, is I don't know what will set those limits in motion, but I think they will happen personally. And therefore, you know, when I showed the level of serfdom and slavery, if that's anything close to reality, and the majority of that is in agriculture, if you can have an agriculture that does most of the work for you, then that's profound if you really are backing out of the fossil fuel dependency. Anyone who's made compost knows, I mean, it's a lot of work. So it's better to not have to compost. Compost is great, but on a really large scale, it's an incredibly energy expensive thing to do. And so the extent to which you can get the ecosystem to do the work just by being an ecosystem, the better we're going to be. And that's kind of how we envision this. With respect to early adoption, it's remarkable to me how fast people adopted Roundup-ready crops in the Midwest. And the thing is if we have an agriculture that regrows itself, is far less expensive in terms of inputs because of its efficiency, and you don't have as many tractor passes and all these things, I think it's going to catch on pretty fast, just for those reasons alone. But I think that we as a species really will need some limits to come up in front of us before we commit to the level of change that we seem to need. I don't know. It's an open discussion. You know.
Malik, anything from you, or one more?
I was going to ask about composting, but I think he's addressed it already.
Important question. One more quick question before we go. Yeah, Austin.
Correct me if I'm wrong, but I noticed that you included a slide in there explaining that it's impossible not to use combines in the Midwest, even in perennial systems, right?
Not impossible. I knew that was going to get me in trouble. It was just the amount of land and the amount of people. I mean, right now, one farmer will farm 5,000 acres, right? And so if any amount of that land goes into perennial production, there needs to be a recolonization of the Midwest and a lowering of lifestyle expectations for human or animal power to harvest a significant percentage of grain. That's a longer way of saying what I was saying. But so go ahead.
Okay. Well, actually, okay. So given that preliminary answer, which was great, does the Land Institute engage with any of those issues beyond just the ecological, which you talked about today?
Yeah, that's a good question. We'd like to, and it has, and I think it will. Is the answer to your question? It has in the past. There was a Sunshine Farm project that went on for 10 years. To examine essentially the energy balance of using draft animals versus biofuel-powered tractors, and could you really get a positive energy return on investment in a modern agricultural system, kind of was the question. And I envision that once we have polycultures that are functional and the grain crops that are a little bit further along, these questions will be squarely in our interest. And so right now we're not big enough to tackle it all, and it's a little premature actually, just because things are not yielding what they will even in 4 years. But stay tuned. Yeah.
Great. Well, let's end there. Thank you, Tim, one more time.